limit. We're not taking a limit.
But you can still slide it over and like.
Yes, you can slide it, but now I've made a mess of this. So I'm just going to leave it. I'm going to move on to the next one.
Whoa. Chain rule.
That's different, right? That's a little different than what we just did. Very subtle, but it's different, right? That's sine of natural log of x, not sine x times natural log x.
Cosine x.
So we have to do chain rule here. The derivative of sine of something is cosine of that something. And then times the derivative of what's in here, 1 over x. Parentheses, parentheses. That's it.
And then you can slide that over.
Yeah, you could just put this like this.
Does it prefer that we go ahead and condense that stuff?
Like this?
Yeah.
Yeah, just do that. Yeah. On the homework, I do that on all of them. I start putting them all together. All right. I think that gives us enough to move into the next concept of this section. And this is a really, really important concept. Really important. Oh, hold on. Differentiation. Okay. Logarithmic differentiation. We have different ways of deriving things, taking derivatives. We have all the rules that we've been using, right? Power rule, product rule, quotient rule, chain rule. These are very important to us. We introduced this idea of implicit differentiation. Remember that? That was a big deal. That helped us with related rates, and we just used it a second ago to prove the derivative of natural log of x is 1 over x. Or natural log, or log base a of x is 1 over x ln a. Okay, we used it. This is a different type of differentiation that we can employ to help us tackle certain types of problems. But they have to fit into a certain category, and you can't really explain it until I show it to you. So take a look at this problem. We're going to start this with an example. Let's say I asked you to take the derivative of x squared plus 1 to the 7th power times 3x minus 1 to the 9th power over 7x plus 2 to the 3rd power times x cubed plus x to the 4th power.
That's a whole bunch of chain rule.
Yeah, this is a disaster if you look at this. It's a disaster. Now, could we do it? Well, we have a quotient, right? So it's just going to be the derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared, right? I mean, we know that that's the format it would fit into. But when it got to going to the derivative of the top, we would have product rule. And then each one of those would require some chain rule, right? Do you see the I'm looking for a good word without using bad language. I can't find one. Cluster. Okay. Do you see this is really not fun? Logarithmic differentiation is perfect for this situation. Perfect, as you're about to see. What I'm going to do is I'm going to take the natural log on both sides of the equation. Just take natural log of the left side, natural log of the right side. So the natural log of the left side and the natural log of this big hunk of junk.
Is that because you can now split that up into each separate columns?
That is because in college algebra we taught you how to condense and expand logarithmic forms, and I'm about to use that to attack this thing. I'm not doing any derivatives yet. All I did was took natural log on both sides. The reason we call it logarithmic differentiation is because we are employing the logarithm to help us with the differentiation. I'm going to work with this as an equation. Left side, right side, left side, right side. Just going to keep writing it down the whole time. Natural log y equals. All right. I have the natural log of division, right? Two things. If I have two things being divided in a single log, I'm allowed to split this into two logs with subtraction. So my two logs are going to look like this. I'm going to have one log right here. It's going to have a bunch of crap in it. This one's going to have a bunch of crap in it like this. And my question is, what's in those?
The top and then the bottom.
The whole numerator is going in here. The whole denominator is going in here.
And then you can split those up again.
So I'm putting x squared plus 1 to the 7th, putting 3x minus 1 to the 9th here. Over here I'm putting 7x plus 2 cubed, and then x cubed plus x to the 4th. That's in that one. Questions? Then I realized that this new log I created here has the product of two things in there. And if you have two things being multiplied inside of a log, you can split that into two logs with addition between them. So my left side is still natural log y, but this is going to be two new logs with addition between them. Okay, so I'm just working with this right here. This is going to become this one and this one, addition. Why is it addition? Because it's multiplication. Okay, so this one gets x squared plus 1 to the 7th. And I can actually put that 7th out here because it means the same thing. That okay? Then this one's going to be natural log of 3x minus 1 to the 9th. I'll put it out there like that.
Do the same thing over there.
Same thing over here. I can split this one up.
But you want to carry the minus.
There you go.
Yep, there's a multiplication, but this minus sign, exactly, very important that if this is going to become two different things, right? That minus sign has to go to both. So you either use parentheses or you distribute the minus as you go. I'm gonna just distribute the minus if that's okay.
I learned the hard way on that one.
I'm gonna put minus here. Are there any questions?
Now you can go ahead and bump up all of those exponentials in front of the logs.
All the exponents, yes. I can go and use one more property. Before I do that, any questions on this? Why these are both minus? Okay, so the last property of, no? Yes? Marguerite? This? Yeah, this right here, this would have been this and this plus, right? But then I would have had that minus out here, which would have had to go to both of them. So I'm going to take this 7 here, use a property of logs to drop it out, 9 here, drop it out, 3 here, drop it out, 4 here, drop it out. And I'm almost to the point where I'm ready to differentiate. I know this seems like, okay, this is taking a long time, but I assure you, this is far easier than us trying to just go after that derivative right away, like straight away. This is going to be much better. Natural log y equals, what do we got?
7 natural logs of that chunk.
That.
Squared plus 1. And then plus not natural log, 9 natural logs.
3x minus 1, right? And then
Minus 3 natural logs. 7x plus 2. Minus
4. Okay. I'm ready to differentiate. Now, why is it that I'm ready now? Like, why not do it like at this step? Think about right now if I asked you to take derivative of this. You would have to do natural log of all of this, right? That derivative, whatever that is. Then the derivative of this to the 7th power. The 7 would have to come out all to the 6th. Then go inside and take derivative of x squared plus 1. That would be a mess to do. But by having the 7 out front now, that's just a constant that's going to come for the ride, isn't it? And that, I'm just taking derivative of that. Derivative of the natural log of something is just 1 over the something, right? Then I have to take derivative of what's inside. 2x, I'd be done. That's going to be clean. That's going to be clean. That's going to be clean, right? They're all going to be clean. But we do have one issue. The other side is natural log of y. So what we're going to do is we're going to do implicit differentiation. We're going to take derivative of both sides with respect to x. What is the derivative of the natural log of something? 1 over that something. Times the derivative of what's in here. What? dy dx, or y prime. When you use logarithmic differentiation, when you use it, the left side will always look exactly like that. 1 over y prime, always. Because the left side is always going to be natural log y.
When we're dealing with logarithmic functions and the exponentials, is it better to keep Newton's notation versus Leibniz?
No. I like Leibniz notation for related rate problems because you have like dv dt, right, with respect to time. Here, I use y prime because it's faster. But there's nothing wrong with putting dy dt, or dy dx, sorry. All right, this one right here. Remember I have 1, 2, 3, 4 separate terms, so I can do a derivative of each one separately, right? So the 7 comes along, 7 times the derivative of natural log of something is 1 over that something. Are we done?
No, 2x.
Times 2x. Because we have to do derivative of what's inside. 7 is coming along for the ride. Derivative of natural log of something is 1 over that something. The derivative of what's in there, 2x. We're done with the first one. What's the next one going to be? Plus 9 times 1 over 3x minus 1 times derivative of what's in there, 3. You go ahead and see if you can get the next ones on your own. I'm just going to write them down. Any questions on that? Did everybody get those last two? Any questions on these? I just started putting things together, right? Like the 3, the 7, the 1, that's 21. And then here, I put those two together on the top. So we're all good? We're not done. We are trying to solve for what? Y prime. Now this piece right here, you're always going to have this happen with logarithmic differentiation. I said you're always going to have 1 over y prime. 1 over y times y prime here, right? Always? And we want to know what y prime is. That means we don't want this 1 over y here. So what should I do to get rid of the 1 over y? Multiply both sides by y. So let's multiply this side by y. It goes away. Let's multiply this side by y, which means that would have to distribute through the whole thing, wouldn't it? So I'm going to put big old parentheses over here like this. Y'all okay with that? So y prime equals all of this junk times y. But what's y? I've erased it. Y was the original function. So guess what you get to do now? You get to replace this y with the original function, which was, x squared plus 1 to the 7th
times 3x minus 1 to the 9th, all over 7x plus 2 to the 3rd, x cubed plus x.
There it is. That is your derivative. Now, if we had done it the other way, we'd probably still be working on it for a while. So the thing, that's it, we're done. That's y, right? Y times that is y prime. 33. No, just leave it. Just leave it. You could. It'd probably cost you a point or so. Because, I mean, all you have to do is just replace the y, right? Just write what y is that's given to you in the problem. I think when we put y in here like this, when we actually replace it, it helps us appreciate just how ugly that derivative would have been had we done it by hand. Because that would have distributed through to those 4 terms, and that would have been a mess. All right, we have one more type of problem that I want to do before we call it a week, right? And that's this one. We're going to call it a week soon. I can almost assure you nobody in here has messed with that function before. Y is x to the x. X to the x. What the heck? I wonder what that looks like. If you were to graph it.
It's a huge number.
I'm going to see how this computer handles it. There it is. Darn it, I was hoping it wouldn't have a graph, then it wouldn't have tangent lines. So we wouldn't have to ask about the derivative. But it does. So what's its derivative? What's the slope of the tangent line on that curve? Does anyone see what the issue is? What the problem, like what the complication of this is? It's not quite this situation, right? Because this worked if the base was like a number, right? And it's not quite this situation because with this, that had to be a number, fixed, x cubed, 5 to the x, right? The 5 never changed. Here, x cubed, the 3 never changed. So it's not quite an exponential function. It's not quite a power function. It is some weird hybrid version of both. And so you cannot do either one of these. You cannot say that this is going to be x to the x times natural log x. That would be using this formula, wouldn't it? Derivative of this is itself times natural log of a. That's incorrect. You also cannot say the derivative of that is x times x to the x minus 1, which would be the rule on here where you drop the n out and then you raise it to the n minus 1.
What if you broke that up?
How are you going to break it up? Yeah. So I just introduced you to this thing called what? Oh wait, we only have 3 minutes? Oops. Oh, I can knock it out quick then. All right. I just introduced a thing called logarithmic differentiation. Right? Take the natural log on both sides real quick.
With respect to x, right?
Not yet though. I'm going to do one more thing first. The reason I did this is so I could somehow use property of logs to make this nicer. I can pop this x out, right? I can pull that power out. And now I'm going to take the derivative, both sides, implicitly with respect to x. So what's the derivative of the left side? 1 over y times y prime. It'll always be that. And then on the right side, very carefully, what is the derivative here? Product rule. Derivative of x is 1 times ln x. So you get ln x plus the derivative of ln x. 1 over x times x, which is just going to be 1. So you get 1 over y prime equals ln x plus 1. Finally, to get y prime by itself, multiply both sides by y. But what is y? X to the x. So y prime equals ln x plus 1 times x to the x. Whew. This represents the slope of the tangent line, doesn't it? So let me just ask real quick. What is a point on this curve? How about 1, 1? Is 1, 1 there? If I plug in 1 here, 1 here, I get 1 to the 1 is 1. So that point lives on the curve. What's the slope of the tangent line there? So come over here and plug in 1. What's natural log of 1?
1.
No. 0 plus 1. So you just get 1. And then 1 to the 1 is 1. So the slope of the tangent line there should be 1. See if it matches. If I go out to 1, I go up 1, I'm right here, right? And the slope of that line is? It is 1. Yeah, exactly. Okay, everyone, we got to end it. Sorry, we got to end it. Why don't you give the homework a shot? 3.3, 3-3. Oh, our next section after this. Oh, we're going to do inverse functions next. Inverse functions. Inverse trig functions. Arc cosine, arcsine, arctan. What are those derivatives? Stay tuned.